Hello, this is Bryant Myers, and welcome to another edition of Debunking Flat Earth. Tonight we got a really good one here. I'm going to go through this pinned comment that Witsit put on his channel under our debate. And he thinks that these responses debunk some of the things that I say. And we're going to go through and, like I said in the last video, we're going to debunk the hell out of all of them. So this is going to be a two-part video. And in this video, I'm going to go through the list of Gleem's sort of responses. And then in the next one, I'm going to go through the 6 citations that Witsit gave me. Because he actually did give me some citations. So that's going to be a lot of fun. So stay tuned for that. Maybe later tonight. Okay, so let's get into today we're just going to go through the questions that Gleem brought up. So let's get right into it here, and you can see, so this is the full list that's on Witsit's channel. So we're going to go through them one by one, and I'm going to debunk them all. So the first one, Gleem is responding to the idea that mass attracts mass, and that electric fields depend on charge. So what Gleem is saying here, that somehow kilograms and coulombs are directly interchangeable according to SI units. Well, Gleem, no they're not. Sorry to tell you this, but if you even if you use what's called a stat coulomb, which is defined, anybody can look this up. You can even sort of you can strip out the K, the constant K from Coulomb's law, and it gives you this kind of what's called the stat coulomb, which is sometimes used in quantum field theory, where they like to set the constants equal to 1, things like that. But even if you get to the most fundamental level, the stat coulomb is still grams. It's basically the square root of grams, the 3/2 root of centimeters, and it's all inverse to seconds. You absolutely cannot convert coulombs to kilograms. It's like converting meters into pounds. I mean, they're just not compatible. So part 1 here of this debunked. So here's the second part to this first comment. Getting deeper, every particle has charge. Even a neutron is a combination of equal and opposite charges to cancel each other out. But essentially, all mass and density of it depends on the charge content. Again, mass is not charge. The two are not interchangeable. This is showing me that you do not understand physics, Gleem. And Witsit says the same thing. I don't know if he's getting it from you or where he's getting it from. But mass is not equal to charge. You cannot convert the two. In fact, when you really look at the energy mass of a proton or a neutron, it's well over 90% from the binding energy of the strong nuclear force. This is a well-known fact, and it might even be upwards to 99%. Now, you can convert mass into energy equals mc squared, but there is no E equals mc squared equivalent for converting charges into mass or charges into energy. That is just a fundamental error that you are using in physics. It's just wrong. Wrong. And then he just kind of goes on about the E equals mc squared. Again, I just answered that. Again, a joule is a unit of energy, a coulomb is a unit of charge. There is no conversion between energy and charge, or charge and mass. Okay, so we already covered that. Now 80%, now he finishes this first point off saying, not forgetting that 80% of the first part of Einstein's Special Relativity in 1905 was reverse engineering Maxwell's equations to make them equivalent applicable to mass. That is absolutely wrong. That is not what special relativity was doing at all. I don't want to get into special relativity in this video, but if he's going to use 80%, that's a pretty specific number, Gleem. I'd love to see a source for that. How special relativity is somehow reverse engineering Maxwell's equations to make them equivalent or applicable to mass. I mean, special relativity was a major revision of Newton's laws that came from the speed of light not being infinite, that had a constant speed. The second part of special relativity is that all inertial reference frames are equivalent as far as the laws of physics go. And this means that all velocities are relative. There is no absolute velocity. So you kind of apply those things and you get a lot of strange things with time dilation, length contraction, and so forth and so on. Okay, let's get to question number 2 here. And this is one that I actually just did a whole video on. So I'm not going to elaborate too much here because I just did a video debunking this whole thing that charges can't be shielded, or that electric fields can't be shielded or electrostatics can't be shielded. So you can see here that Gleem is responding to, of course, me saying that charges and electric fields absolutely can be shielded. So he says that you're neutralizing charge, not removing it. There's always background radiation in every experiment, no matter if you're miles deep beneath the Earth's surface or in the thickest mu metal box. Where there is moving matter, there is charge. Even deeper, you have the ether or zero-point energy, which has more evidence it exists in things like the Kashmir effect, Lamb shift, vacuum bifringence. Okay, he kind of goes on and on. Yes, these are all quantum effects, and you, like Witsit, just like to rattle off these words from quantum mechanics, not really knowing what they mean. You absolutely can shield electric fields. And even if you invoke quantum mechanics, if you use quantum electrodynamics and draw your Feynman diagrams, guess what's going to happen if you put a Faraday cage around a charge? Those Feynman diagrams will end up all becoming extinct beyond the Faraday cage wall. And again, they're just continuing to misunderstand that there is a difference between charge and energy. And vacuum energy, you can't convert that to charge. It's not the same thing. So just fundamental errors in physics. They just don't understand fundamental electrodynamics, let alone quantum mechanics, which you don't even need quantum mechanics here. I mean, Maxwell's equations are enough, especially when you use Coulombs law. Just simply Coulombs law is enough to show that electric fields are blocked when you surround them by a conductor. And again, I'm not going to go through, I went through this in detail in my last video, but you absolutely can shield electric charges and electric fields. And again, it's provable and measurable. You can get the most accurate electrometer and you'll see that the electric fields are shielded. And again, these rooms that I showed in my last video, there's hundreds of them out there. So people would literally be levitating or they'd be in a zero-G environment inside these shielded rooms if the downward bias or the source of the downward acceleration came from electrostatics. Okay, so let's get to comment number 3 here. Okay, this is a good one. I'm going to play a little video here. So why don't objects with different electric charge or magnetic properties fall at different rates? So you have never heard of Boyd Bushman from Lockheed Martin, who dropped a rock in a massive dual magnet painted like a rock of exactly the same mass, and in his repeated experiments, the dual magnets always fell after the standard one. This was signed off as witnessed by many other scientists, and there's video footage of this on YouTube. Okay, now, it's worth noting that this guy, you can see pictures of him that he's sort of evidently been in contact with aliens, and he showed images of this. And somebody online actually exposed that image of the alien was a plastic toy, as you can see here. Okay, but let's just forget about that for a minute. Let's just pretend that Boyd Bushman's experiment is worth looking at objectively. Just one little note here, and I used to do these experiments when you drop a magnet through like a metal tube. It's called Lenz's law. The eddy currents from the Faraday induction will oppose the falling magnet, and it will fall really, really, really slow. And again, these little toys, you can buy them on Amazon. You can show this to yourself. And the problem with Bushman's experiment, that he was dropping them off of a multi-story building, and there was probably steel beams there, so all these little eddy currents going on and opposing forces. So this was not a carefully controlled experiment. And the video, I want to play a video right now from Action Lab, a really good YouTube channel, where he does this experiment very carefully and shows that there is no difference in the falling rate. So let's watch and see what he has.
2, 1. Now let's look at them both dropping exactly together. My start time is measured from when the plunger end of the syringe passes the red line, and the end time is when it hits the bottom. And I get that they hit the ground at almost exactly the same time, within 1/1000th of a second. So although Boyd Bushman claimed that if you push two magnets together, they'll drop slower, I don't see any reason why in physics that would happen. And also experimentally, I don't see it happen either.
Okay, so that's a really good little video clip, and he took more care than Boyd did. And here's the thing, he actually then did a little experiment after this where he weighed them, because again, if it would fall slower, then there should be some opposing forces, which would make the weight of these opposing magnets way less. And if you get a really, really accurate scale, you'll see that they don't. So totally debunked. Okay, next point. Okay, so the next thing he said is bringing up the fact that I bring up that everything falls at the same rate. So he says, what experiments have you done, peer-reviewed, have actually demonstrated this? As I am pretty sure that Einstein's relativity, the Earth is coming up to meet the apple. Meaning the greater mass is doing the acceleration and the objects are levitating in midair. Now, this is kind of laughable. And I did a video, my first video in this debate review series, on the constancy of gravity. Actually, geodesists have mapped out the gravitational acceleration across the planet to incredible detail. You know, absolute gravimeters go out 9 digits. The acceleration into gravity varies between like 9.764, something like that. It's more detailed than that, but just roughly up to 9.83 something. A very narrow range. It's only 0.7% difference across the planet, provably, and this is at the surface, of course. Yes, you could say in one frame of reference the Earth is coming up to meet the object, but again, how big is the Earth? It's ridiculously large. But for all practical purposes, and when we use the Earth as an inertial frame, we're always using the center. We're always using the center of mass of the Earth, things falling towards the Earth. It just makes a lot more sense. But again, that doesn't prove anything anyway. Things still fall at the same rate. Oh, and just worth noting that Walter Bislin commented this on my first video, and the variations when Witsit brought up the whole weather thing during the debate, he was making it sound like the weather was wildly changing the accelerations or changing them significantly. It's actually like 7 decimal places. It's hardly any impact at all. So all this stuff about the weather during the debate is just total nonsense. I mean, not that the weather doesn't affect gravity. It does. But it does so very, very in a minuscule way. Okay, next point. So this is getting to the fact that gravity is always attractive. So here he says, so gravity makes everything with the mass attract everything with lesser mass in the vicinity. So in the real world, we record the moon to be moving away from the Earth by 4 centimeters per year, and the Earth-Moon system moving away from the sun by 12 centimeters a year. Not only this, but even the 2011 Nobel Prize was awarded to discovering that every piece of large matter moving away from everything else, known as the cosmological constant of dark energy. This, my friend, is repulsion you deny the net system has. However, you prefer to state that gravity is attracting everything else, and it's unidirectional. Well, gravity is always attractive. So let's just take this one point by point. So the first point I just want to talk about, we actually learned that the moon is moving away from the Earth a little bit by bouncing lasers off the mirrors that both the US and the Soviet Union installed. So again, you bringing up that point kind of debunks your whole moon landing thing, because that's how we discovered that it is moving away. This slowing down is partly due to tides, which cause kind of a drag on the Earth-Moon rotation. And this kind of slows down the angular momentum, which is why the moon is slowly going away. And similar effects are happening with the Earth-Moon system with the sun. So it's all explainable by our current model of science. And I did a video to address your last point about the cosmological constant, dark energy, dark matter. And I'll put a link below this video where I kind of go through these objections, meaning in our inertial frame of reference, neither dark energy nor dark matter affect the laws of physics as we know them. And so what we observe within our inertial frame is mass is always attracting mass. Okay, let's get to point number 6 here. And this is, I kind of get into electromagnetic attraction and how pretty much all of bulk matter is neutral, which it is. So there really isn't that much electrostatics going on. So he says the principle of least action is at play here, where all matter may be considered neutral, but if you apply an intense and balanced positive charge to one side of you, it can rip of your skin or attract it so much that it physically embeds itself in your skin and burns you. Then he goes on to talk about how refrigerator magnets are defying the sum total of the force of gravity of the entire Earth. Okay, this is kind of a dumb comment. I mean, of course, if you apply a lot of charge to your body, you're going to get electrocuted or burned. But that doesn't take away from the fact that most things are electrically neutral. Electrostatics is really only happening in our daily lives when we rub our socks on the carpet, or we static cleaning in your dryer, or when you comb your hair, sometimes you can get some static electricity there. Of course, lightning is an example of static electricity. But what you're saying about applying charge and getting burned, I mean, this is not this is in no way contradicting that most things aren't neutral on the bulk scale. This is just a stupid comment. And again, I'm going to put a link below this video on my flat earth quote unquote science, where I did a whole video showing that flat earthers just can't seem to draw a free body diagram to save their lives. So when you put a magnet on a refrigerator, it's got more than one force acting on it. So you have the downward force of gravity, and then you got the force of magnetism, those two main forces going on here. And the force of magnetism is stronger than gravity. So what? It's not anti-gravity. That's just the electromagnetic force. It's just a dumb comment. And again, I don't even think that you understand what the principle of least action is. I won't get into that here, but you got to set up an action integral and minimize kinetic energy minus potential energy or cross the path. It absolutely has no application to this question. Okay, let's get in, this is a good one. Let's get into question number 7 here. So again, this is something that I brought up in the debate. I'm like, so you're saying the acceleration of the gravity is a downward bias. What do you mean by that? You mean just an arrow with no magnitude? Show me in nature where there's a force that has just an arrow or direction only. So now, so Gleem says, didn't hear what you meant by this, but use a scalar field and they are much better conceptually. No, that's wrong. That's bad physics. You don't use a scalar field. A scalar field is not... These guys really don't understand science. I mean, they just throw out words and hope that people listening don't know science. But when you have a physicist, Gleem, look at your nonsense. I do see this stuff and I do understand it. And you are just, it's just a bunch of baloney. I mean, I honestly don't know how people are believing this stuff. Scalar fields are magnitude only. Scalar fields are the opposite of what you're saying. They're just pure numbers. So a temperature field, for example, scalar field, you got just a number at every point in space that you're looking at. Altitude fields, like on the Earth, you could define a scalar field for all the altitude points on planet Earth. And basically what it is just a pure number, no direction at every point in space and time. So you can say at this point, this is what the elevation is are all across the Earth. But now here, where do you get a vector from a scalar field? You take the gradient, which is the vector version of a derivative of this scalar field, and that will, when you take the gradient of the potential, or the scalar potential, then you'll get a force, then you'll get an arrow. But that arrow is not an arrow only, it absolutely has a magnitude and direction. In fact, you can do that with gravitational potential energy, take that elevation map and take the gradient of that field, because again, gravitational potential energy is just mgh, so it's pretty much just based on elevation. But you're not going to get a scalar only, you're not going to get an arrow only, you're going to get both a magnitude and direction, which will match and confirm what we know as the downward force of gravity. Sorry, this is terrible science. You really don't know what you're talking about. And let me just to mention here that I use the weather vane analogy because a weather vane is just showing you direction of wind. But the irony is that wind itself is a vector field because vector fields have both a magnitude and direction for every point in space that you're looking at. So wind, even though you can use a weather vane to see just the direction the wind is going, the wind itself actually has both a magnitude and direction. There are no pure arrows or pure direction only vectors in science or in nature. The only thing is a unit vector, but that's just mathematical. Or you could say north, south, east, or west, but again, that's not giving you any physical, it's not describing, any physical property. Gravity and the downward acceleration is a vector. It has both a magnitude and direction. You can't just say downward bias. That's just a bunch of BS. Okay, number 8. And this wasn't even one of my biggest points, but the fact is that the conductive properties across the surface of the Earth are different, which should give rise to different electric fields over different areas, depending on the ground, ocean versus land even, big things like that. So he goes on to say that it doesn't change how we are able to detect metals, oil, and water underground using radio waves. you will find that there are certain petrification of sand called fulgurites, which literally drag the sand up and fuses it. Now, if that's not defying gravity and demonstrating that there is 100% a difference in effect from this making the force change, then nothing will convince you. Even deeper, the basic foundational method where we found the electron's charge, the Millikan oil drop experiment, the physical demonstration is defying gravity with X charge, I don't know, I think it just means X-rays, making droplets of oil levitate with electrostatic charge, and in cases shoot upwards with increases in charge. Okay, again, more misunderstandings, not understanding free body diagrams. I'm going to put a link again below this video to my flat earth science. So hopefully Gleem, Witsit, you guys can understand what a free body diagram is. But on the first point, I don't even know why detecting things with underground radio waves has anything to do with this. The point is the electric field across the planet changes with location, much, much more than 0.7%. Around thunderstorms, it changes wildly, changes by time of day, by season, and I've done a whole video on that in my video number 2 in this series. Now, when it comes to fulgurites, the upstroke of lightning, again, there's other forces at play here. I mean, there's, just thinking that there's only one force and that anything that seems to defy this is anti-gravity is not understanding a free body diagram. And let's go through the Millikan oil drop experiment. The main thing with the Millikan oil drop experiment, you had an applied, because again, electrons have charge. So you had an applied voltage going up that caused, it to slow them down or go the other direction. But again, this is not levitation. This is the electromagnetic force. And again, it's the same thing I can do when I take a comb and comb my hair, and I can pick up little paper filings because of the electrostatic force. It's not anti-gravity. The gravity is still acting there, but the force of gravity is just a lot less than the force of electromagnetic force, which is why it goes up. Again, you guys don't know how to draw a free body diagram. Please watch my video number 4 in this series, which I'll put a link below. Okay, last question. We're down the home stretch here. Okay, this is the one around the thunderstorms. And again, MC Toon and I really debunked the heck out of this in our sort of funeral service to incoherent dielectric acceleration. And so he says the net effect of the magnitude to levitate the average person would take about 1,000,000 volts right beneath their feet. Certainly enough to kill them, but not enough to sustain them levitating unless millions of volts are continuously applied. I have had the fun experience of having my hands in the washing machine when someone switched the wrong switch and I was electrocuted and flung across to the other side of the kitchen. If you think this was controlled and I could have just not been thrown back and just took it like a man, I beg you show me connecting themselves to 240 volts main supply and not have a change in force also. I was not magneto and levitating around the house for the rest of the day, but I know how minds wander. Okay, so kind of going through this. Now, if you're going to say the 100 volts per meter causes the downward bias of why things accelerate down, then using that logic during thunderstorms, even if the thunderstorm was the same voltage but reverse directions, things should be levitating up at the same acceleration going up. You can't just say downward bias and use 100 volts per meter without invoking Coulombs' law. Coulombs' law will tell you if you turn that around, you're going to get 150 times the level of the electric field, and things are going to go upwards 150 times more than they were going downwards. And again, even if it was a bias, they're going to still reverse and go the other direction. You can't change the rules to suit your contradictions. Again, you have to be consistent with what you're saying. This is, again, I said kettle logic. This is absolutely, you're contradicting yourself in different situations just to suit the needs and prove a failed model. Now, the whole thing about getting flung across the room, it was Luigi Galvani that first saw that when you electrocuted frogs, that their muscles would twitch violently. So what's happening there is that when you got electrocuted, your muscles twitched and that threw you back because of your muscle spasm. And this is something that does happen when people get electrocuted. But it's nothing to do with anti-gravity at all. Nothing to do with any gravitational effect. It's purely electric in your muscles causing the contraction. And I had the situation where, a little bit different, where the lightning struck me just 6 feet away. And I didn't turn around and levitate, go up, and I was definitely within that polarity reversal. But the acoustic shock wave from the lightning kind of threw me back a little bit. But that's not anti-gravity, that's just acoustic shock wave, because when you have lightning striking, the pressure wave from that strike is very powerful. That sound wave is incredibly powerful. But again, it's all explained by science, Gleem, Witsit, and our current science debunks the hell out of the flat Earth gravity model of incoherent dielectric acceleration. It's a dead model, it fails, it doesn't work, and you've really got nothing, guys. So stay tuned now. It's not, let the debunking continue tomorrow evening, because I'm now going to go through the 6 citations. I mean, Witsit finally gave me some citations, and I'm going to go through those and just demolish them, because he thinks that they're proof of electric gravity, and they're actually studies. Some of them are just laughable, but there's a couple that are decent, but they don't even really prove his point, as we'll see. So stay tuned for that, and I thank you for watching. I hope you have a really great night. Please do like this video, leave some comments, and subscribe to my channel. I have many more coming.